Welcome to Maths with EJD. I've been talking about basic calculus lately, and I've made a whole lot of videos covering functions, limits, continuity, differentiation, applications of differentiation, and then integration. So at this point, we'll move on to talk about the applications of integration. And on this note, we'll be looking at those applications in four areas in the areas of in the areas of areas, kinematics, probability, volumes. So four applications of integration. Of course, there are other applications for sure, but then these are the four we'll be focusing on in this case: areas, kinematics, probability, and volumes. So I'm going to make each video for each area of application. So let's go straight to talk about areas. Talk about areas. Of course, as you know, depending on what you are looking at, area is a two-dimensional thing, right? If it is for a square, you have length times length. If it is for like a rectangle, you have length times breadth, and so on and so forth. So it's at the end of the day, the unit is in square it is in square units, whatever it is, maybe square meters, square kilometers, and things like that. That's what area is about. So how does integration apply to areas? So first of all, we can talk about area between a curve and the x-axis. So basically, most times when you're integrating functions, you can be it's basically areas you're looking for, right? So we can compute the area between a curve f of x and the x-axis with specified limits x equals a and x equals b by computing the definite integral defined by this. So each time you compute a definite integral like this, and it's just the function alone, without being multiplied by some other function, then you are basically looking for area. So technically, each time you integrate something, you are looking for area under in a particular region like that, except in other cases where maybe you multiply two functions together and things like that. So it is always helpful to sketch the curve in order to have a clear picture of the problem. So most of the times, if you do not sketch the curves of the questions you're given, you do not get to see a clear picture of what you're doing. So it's very important to sketch the curve first so you can know what exactly you need to integrate. So only the absolute value is considered as area. Of course, since there's no negative length, so technically you cannot expect to have negative area also. So you talk about absolute value. So if you're calculating area and you get a negative value, you just take the absolute value, you ignore the negative sign. So as such, we ignore negative signs when they arise in our calculation for areas. That's really important to take note of. Okay, so let's go ahead and talk about our first example. Find the area of the region between f of x equals x squared minus 5, the x-axis within the limits x equals minus 2 and x equals 2. So you have f of x equals x squared minus 5. So if you plot x squared minus 5, this is what you get. This is what you get. X squared minus 5. That's exactly what you get. But then we want to calculate the area between it and the x-axis. You see, this is the x-axis. So you have this, normally normally it should go up that way and go up this way. But then we want to find the area under it, the x-axis, and the limits between minus 2 and 2. That's why we have just this region, out like that. So like I said, if you do not plot this, you won't get a clear picture of what you need to do. So that is it. X squared minus 5. This is it. Of course, you can see this is starting at minus 5 around here. So this is a parabola that passes through minus 5 because at x equals 0, y will be equal to minus 5. And that's exactly why you have it passing through this point. And then it should go up, normally quadratic, go up. But then you're concerned about what it is like between minus 2 and 2. So once you're able to plot that properly, then it's easier now to integrate to get the area that is required of you to get. Okay, so the next thing is, since you've uh, put that out clearly, the next thing you want to do is to compute the area. So the area is computed as follows. You have integral from minus 2 to 2 of the function f of x, which is x squared minus 5 dx. So, and then that's pretty easy. Integrate x squared, you get x cubed over 3. Then integrate 5, you get 5x, and that's between minus 5 and minus 2 and 2. And then, well, you can do it together, but I like to split it up so things can get really easy. So yeah, so you can have x cubed over 3 from minus 2 to 2, and then minus 5x from minus 2 to 2. Then I even go ahead to take the constant out to avoid it disturbing us. So you take you take 1 over 3 out. So you can focus on just the x cubed that the minus 2 and 2 will be taken over from, taken over. And then you have 5 into x like that. And you evaluate at 2 and minus 2 also. So getting that out, so x cubed will now be 2 cubed minus 2 raised to power 3. The first 2 is the 2 at the top, the upper limit, that's 2 raised to power 3, and minus 2 raised to power 3. Then the same happens for 5x. So you have 5 into 2 minus 2, and that means you have 1 over 3. 2 raised to power 3 is 8, minus 2 raised to power 3 is minus 8. Then here you have minus 5. Then this is 2 minus 2. Then we tidy things up and we have 1 over 3, 8, minus times minus is plus 8. Then minus 5, 2, minus times minus is plus, and then you have 2 like that. So now you have, of course, 8 plus 8 is 16. So 1 over 3 times 16 is 16 over 3. Then 2 times 2 plus 2 is 4. 4 times 5 is 20. So you have 16 over 3 minus 20 over 1. LCM, of course, is 3. 3 in 3 is 1 times 16. That's 16 minus 1 in 3 is 3. 3 times 20 is 60. 16 minus 60 is minus 44 over 3. So you have minus 44 over 3 square units. And of course, since we are dealing with area cannot be negative. So we ignore the minus. We take the absolute value of this. And at the end of the day, we have 44 over 3 square units as our answer. And that's how you compute such an area. So, the kind of integral you're going to evaluate depends on the unique situation you have. So that's why it's always important to sketch the curve first of all. So look at what happens here. So you want to find the area of the region between f of x equals sine x. You already know that sine x is of course, when we say something is sinusoidal, right? It passes through the origin, so it reaches the peak of 1, and then it goes down, reaches minus 1, and it keeps going like that, it keeps going like that. So, but here we want to find the area of the region between f of x, which is this now, that keeps going up and down like that, and the x-axis within the limits x equals minus 2. So x minus 2 and x plus 2. So we are interested in this region. So you discover that these are two different regions. So it will be wrong for you to just integrate like that. It will be just difficult to say f of x dx from minus 2 to 2, because you will see that these two regions are totally different. That's why I color coded this. You have the green region here. So the green region is defined between minus 2 and 0, and the purple region is defined between 0 and 2. So since it's not the one side like that, so you need to carefully present the integral. So you see that the green region is between minus 2 and 0, right? So you say integral from minus 2 to 0 of sine x dx, because it is still sine x, right? Between minus 2 and 0, all right? So you have that. Now, so this is an area on its own. This is another area on its own. So you have to do the two and add them together, because they do not overlap. So we are going to see cases where things overlap, and then we have to separate those accordingly. So here, of course, I put the absolute sign to show that whenever it's negative, we don't care, we throw away the minus sign. All right, so now you have integral from minus 2 to 0 of sine x dx, and then you have 0 to 2 of sine x dx. Of course, this is the 0 to 2 part, 0 to 2. This is minus 2 to 0. So you have it in two parts. So if you do not sketch this, it will be difficult to know exactly that it should be actually this way, So it's important to think about that. All right, so if you integrate sine x, of course, that's minus cos x, and that's from minus 2 to 0. And if you integrate sine x, you get minus cos x now from 0 to 2. So now it's broken apart, unlike what we had before, that I just integrated everything all together from minus 2 to 2. It won't work like that here. So we have minus cos x from minus 2 to 0. So take out the minus, you have minus cos x from minus 2 to 0. Same here. And then So now that the minus is out, so you can say cos 0, you have cos 0 minus cos minus 2. And of course, you already know that cos is an even function. So if you cos minus 2 is the same thing as cos 2. And that's why you have cos 2 here. This still remains cos 0. And of course, the same. So here you have cos 2 minus cos 0, like that. And then we try to tidy things up. You have cos 0 is 1, you know, on that, when I get teach trig, I'll explain to you. I think I've mentioned this idea of special angles before. Angles like 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So you don't have to look at calculator or look at a table before you get answers to maybe sine, cos, tan of any of these special angles. So 0 is one of such angles, and you should know that cos 0 is 1. So that's why you have 1 here, 1 minus cos 2, then cos 2 again. Now, what is happening here is this. So we take this minus out. So this minus and minus becomes plus, so that, this change switches over, So basically, we have minus cos 2 minus cos 0. So if you take minus out of here, right? So it's more like you have minus into minus. So if you have minus outside, that's like minus cos 0 minus cos 2. So take this minus out, and so you have plus into cos 0 minus cos 2. And that's exactly what we did here to get this to be plus 1 minus cos 2, like that. Okay, so you see that the sign outside changes. So here the minus has been factorized out. So minus times minus is plus. So you have 1 again minus cos 2. But then we're interested in the absolute values, right? So if you find the absolute value of minus 1 into 1 minus cos 2, you get 1 minus cos 2. And here you also get 1 minus cos 2. So that's like 2 into 1 minus cos 2. That's like 2 into 1 minus. So cos 2 is minus 0.4161. So that's 1 plus 0.4161. And that's 2 into 1 plus 1.4161. And that is 2.8322 square units, So where you are going to get into trouble is this. Once you don't do the breakdown well, so you need to draw your diagram well, and then you need to break it down properly, like you have seen. Okay, so now sometimes you also need to talk about area between two curves, right? So given two curves f1 of x and f2 of x, with the first curve above and the second below, we can compute the area in square units between them using the definite integral. So this is the definite integral. So the function above, now how do you know which one is above? You have to sketch the curves so you can know which one is above and which one is below. So whichever one is above will come first, then minus the one that is below, and then you do the integral between a minus a and b. A and b are the points where they intersect. So if the curves intersect, a and b are the points of intersection. And sometimes to get the points of intersection, you may need to solve for f1 of x. Just equate f1 of x to f2 of x. And then you can get the points of intersection A and B where the curves intersect. So the functions can also be equated and solved to obtain A and B. That's what I've just explained. So if the curves do not intersect, the limits A and B must be specified. So if it's either the curves intersect or the limits are specified, like we had the -2 and 2 thing we talked about the other time. Okay. So, I mean, another case would have been to find the angle, the area covered by sine x between the sine curve and the x-axis. So that would be wherever the sine curve cuts the x-axis. So it becomes absolutely necessary to sketch the curves for the sake of accurate interpretation. So if you do not sketch the curves, you won't be able to interpret accurately so as to know which function is at the top and which one is below. So let's take some actual examples to drive this point all the way home. Okay, now look at this. We want to find this now. Find the area of the region between f of x equals x squared minus 5. We've come across that before. And f of x equals 1 plus x. Clearly, this is a quadratic expression and this is a linear expression. So you never can tell which one is above or below until you sketch, like we said. And to sketch 1.5x, right, this is it. Like, this is the thing. You have, say, of course, this is 0 here. You have 1, 2, 3, 4, and so on and so forth. So at x equals 0, right? At x equals 0, then, okay, at x equals 0, then y would be 1. Let's say 1 is around here. So if you put 1, at x equals 1, y is 6, somewhere around here. Y is 6. at x equals 7, that's at x equals 2 rather, that's y will be 11. Let's say 11 is somewhere around here. So you have 11 here. And of course, for a straight line, you need only 2 points to sketch the curve. So you just have that going all the way up. And then for x squared minus 5, you know that at x equals 0, the function, this will be 0, and you have minus 5 left. So you have minus 5. So this, and of course, you already see that that's a parabola. So, it's going to be something like this, and it goes. So these two have points of intersection here. So you can see we have not been given the points of intersection, but we can actually get that by equating the functions and solving to get the points of intersection. So from here now, you see that the straight line is above the curve. The straight line is above the curve. So in that case, the next thing you need to know is you already know that the integral should be from a to b of f1 of x minus f2 of x dx. And in this case, you don't know which one is F1 or which one is F2. Oh, okay, now we know, right? After sketching, you discover that this is F1 of X and this is F2 of X. This is F1 of X because it is above, it covers up the parabola, right? So that's what we have. So the next thing is to find A and B, that's the interval. And since they intersect even from the plot, you can actually find their points of intersection. First, we find A and B by equating f1 of x. So we take f1 of x to be 1 plus 5x because there's a curve above. Well, it's actually the line above. And with f2 of x, which is x squared minus 5, which is the curve below, such that f1 of x equals f2 of x. So you have so that's 1 plus 5x equals x squared minus 5. So that means collect like terms. So you have x squared minus 5x, then minus 5 minus 1. So you have 0 equals x squared minus 5x minus 6. So you can factorize this. You need two numbers. When you multiply, you get minus 6. When you add, you get minus 5. And those two numbers must be factors of 6. So, and of course, we know 2 and 3 will do that job easily. Since you need minus 5, so it has to be minus 2 and minus 3. And if you have, okay, well, okay, minus 2 times minus 3 will give you plus 6. So that's not correct. So it has to be, so you need two numbers. When you multiply, you get minus 6. So, and since you're looking for minus 5, so it has to be also 6 and 1, which are also factors of minus 6. So minus 6 times 1 will give you minus 6. And minus 6 plus 1 will give you minus 5. So that's why you have x squared minus 6x minus 1x, which is minus x, minus 6 equals, so x into x minus 6 plus 1 into x minus 6. So you can factorize that. You have x plus 1 into x minus 6. That's exactly why we have this expression. Okay, so now you can see that the point of intersection of those two curves will be x equals minus 1. You can take that as your A because it is a smaller value, and x equals 6, which you can take as your B. So now you have your A and B, the limits. So all you need to do now is to just integrate away and get the area between the two curves. So now the area is computed as follows. You have f1 of x, which is 1 plus 5x. You have f2 of x, which is x squared minus 5. So don't forget the minus. And then you have minus 1 to 6, which you have found by solving for the points of intersection by equating the two functions. So you can open this up. So you have 1 plus 5x minus x squared. Minus times minus is plus. So plus 5. So you add things up. You have 1 plus 5 is 6. 5x minus x squared. So now you can integrate. So if you integrate 6, you get 6x. If you integrate 5x, you get 5x squared over 2. If you integrate x squared, you get x cubed over 3. Integrated between, evaluated within the interval minus 1 and 6. So like I like to do, take out the constant so you can have easy access. So you have 6 out, you have x evaluated from minus 1 to 6. You have 5 over 2 out, you have x squared evaluated from 1 to 6. And you have minus 1 over 3 out, then x cubed to be evaluated from minus 1 to 6, like that. Okay, so now things are easier. So you have 6 outside. So you have, if you put 6 for x, you have 6 minus minus 1. Then you have 5 over 2. This is x squared. So that's 6 squared minus 1 squared. Then minus 1 over 3. You have 6 cubed minus minus 1 cube, right? So we can tidy things up further. 6 plus 1 is 7. So you have 6 times 7. 5 over 2. 6 squared is 36. minus, this is 1. 36 minus 1, that's 35. And this is 6 cube is, I think, 216. I think 216. Then plus, this is minus minus 1, that's plus 1. So that's why this is 217. So if you do all of that together, right? You have, this is 42. You have 42 plus 105, I believe. 35 times 5 should be 105 divided by 2, then minus 217 over 3. So if you find the LCM of this and do it all together, you get 343 divided by 6 square units. And that is an example of area between two curves. So sketching is important. I mean, that's sketching correctly. That's extremely important. Okay. So let's talk about this other one, this beautiful violin shape. Look at what we have. So in this case, you want to find the area between the region. See, this same expression has followed us here. So you want to find the area between the region, between f of x equals x squared minus 5, right? And f of x equals sine x. So, and now we are specifying from x equals minus 2 and x equals 2. Even if they intersect, once you are given the limits, you have to follow the limits, all right? So even if they intersect at some point, you don't care as far as you have a limit given. And if you don't intersect too, once you have limits, just follow that. So you'll discover that, if you sketch this curve, right? This is sine x now. This is what your sine x looks like. That's what keeps going up and down like that. And then for the other one, x squared minus 5, that's that parabola again that goes through minus 5, and normally should keep going like this. You can see they actually intersect, but it has been specified to you that that you should evaluate them between minus 2 and 2. And that is exactly what you do. So this is the region you are interested in. So you have to pay attention to the things you are given. All right. So so if you remove all of that, this what you end up having. So again here, you can see that sine is above. So that's like your f1 of x, while the f of x equals x squared minus 5 is below. That's your f2 of x, like that. So it means that sine x is going to be first and then minus f of x, which is x squared minus 5. And then we have been told it's between minus 2 and 2. So we go for that. So here we have the area is computed as this integral from minus 2 to 2 of f1 of x minus f2 of x dx. And then we know already that f1 of x is sine x because it is above, according to the diagram we have, minus f2 of x, which is x squared minus 5 dx. So that's sine x minus x squared plus 5 if you open that bracket up. And then if you integrate sine x, you get minus cos x. Integrate x squared, you get x cubed over 3, which is the same thing as minus 1 over 3 x cubed. Integrate 5, you get 5x. You don't worry about the constant because it's a definite integral. And, when you evaluate at those values, the c will cancel out. I showed you how that happens previously, okay? All right, so now you take each one, you have minus cos x. You can actually do everything together, but I think I just like to come to the individual level to make things as clear as possible. So you have minus cos x to be evaluated from minus 2 to 2, then 1 over 3. I've taken the minus 1 over 3 out already, and you have x cubed to be evaluated from minus 2 to 2, and you have 5x from minus 2 to 2 like that. And then we keep going. So here you have minus cos 2 minus cos minus 2, like that. Don't forget, cos is an even function. So, and what that means is that cos of minus 2 is the same thing as cos 2. I talked about this when we're talking about types of functions, right? So you have minus 1 over 3 into 2 cubed minus minus 2 raised to power 3 also. And then you have 5 into 2 minus minus 2, like that. And then we firm things up better. So like, the cos is an even function. So cos 2 minus cos, so cos minus 2 is also cos 2. And then you have minus 1 over 3. 2 raised to power 3 is 8 minus 2 raised to power 3 is minus 8. So that's 8 minus minus 8, which is 8 plus 8. And here again, you have 5 into 2 plus 2. And then this is cos 2 minus cos 2 is 0. So all these parts will go. So you have 16. So you have 0 minus 16 over 3 plus 20. So minus 16 over 3 plus 20 over 1. LCM is 3. 3 in 3 is minus 1 times 16 minus 16 plus 1 in 3 is 3. 3 times 20, that's 60. 60 minus 16, that is 44 over 3 square units. And that is how that goes. So that is the application of integration in getting areas, whether area of a curve within certain limits or area between two curves. And if you need questions to try your hands on, let's go for them. So this we have talked about areas here, right? So you can find relevant questions. So the first two questions here deal with areas. Okay, so you can try your hands on this. So after everything, I'm in the last video, I mean, maybe the video for the last application of integration, I'm still going to show all the exercise, but for now, you can focus on this first two exercise. So if you have not subscribed, make sure you do that. Press the notification bell so you can always get alerted when a new video is released. Thank you for listening. See you in the next video.